Number 8. Land west of the San Andreas Fault in Southern California is moving at an average velocity of about 6 centimeters per year northwest relative to land east of the fault. All right, so before we move on, let's just draw a quick picture. So here is the San Andreas Fault. And it says that land mass that is located to the west of the fault. So I'll draw this little box here. Remember your coordinates, north, south, east, and west. This particular landmass is moving at an average velocity of 6 centimeters per year northwest. So it's moving in this direction. So that is 6 centimeters per year. Yeah, right, relative to the land east of the fault. Okay, next sentence. Los Angeles is west of the fault. Okay, so let's consider this LA. And may thus someday be at the same latitude as San Francisco, which is east of the fault. Now, knowing San Francisco lies also to the north, you need to know a little bit about U.S. geography here. But San Francisco lies also north of Los Angeles. So it's saying that eventually, someday, this landmass of Los Angeles will eventually be at the same latitude, right? Remember, latitude's horizontal. It'll be at the same latitude as San Francisco. So now it says, okay, how far in the future will this occur if the displacement to be made is 590 kilometers northwest? So in order to get to this latitude, it tells us that the landmass here, the Los Angeles landmass, must travel 590 kilometers. Okay. So, and they want to know how long it's going to take. So I'm looking for time, right? They gave me a velocity, average velocity. They told me that it was 6 centimeters per year. And then they also told me the displacement value, that it was 590 kilometers. Now think about a relationship between these three variables. Do you know one? Mathematical relationship, that is. Not a romantic one, but a mathematical one. We do, right? So the velocity, average velocity, is equal to the change in displacement divided by time. Okay, great. So it seems like we have everything we need. Let's plug it in. So we have 6 centimeters per year for the velocity. The displacement, right, or the change in displacement, they told us was 590 kilometers. And then divide that by the time value. And as long as I know 2 of the variables, I can always solve for the third one. Okay, so it sounds great. So now we're just going to calculate and solve. But wait a minute. We can't yet do that, right? Because the displacement units here in the problem are not consistent. They better be consistent, otherwise your calculation will be wrong. Now, I don't care if you convert this value into kilometers or you convert this value into centimeters. As long as they're both the same, that's the important part. That's the important point. So I think it might be easiest to convert this value into centimeters. So I'm going to do that on the lower left-hand corner. So 590 kilometers. I put kilometers on the bottom, meters on the top, because I know that there are 1,000 meters in 1 kilometer. That gets rid of the units of kilometers. Then meter goes on the bottom so I can cancel it. And now I do know the relationship between meters and centimeters, which is 100 centimeters in 1 meter. So the meters cancel. So now take out the calculator and plug it all in. Right, so we get 590 multiplied by 1,000 multiplied by 100. And the answer comes out to be 5.9 times 10 raised to the, let's see, 7th, it appears, times 10 to the 7th. And that is centimeters. Okay, great. So I have 2 sig figs here because I started with 2 sig figs. There's no decimal, so the trailing 0 does not count. Okay, so now let's take this value and plug it back into my equation for the displacement. So let's rewrite everything. So we have 6 centimeters per year will equal 5.9 times 10 to the 7th centimeters over time. So now everything's consistent, I can solve. Now just remember, when you solve for time here, the time will be in years, because that's the unit of time in the velocity. Okay, so I'm just going to get rid of the units now, just keep that in mind. I'm going to get rid of the units just so I can clean it up a little bit, so it's a little easier to follow. All I'm going to do here is just now switch these two variables, bring the time up to the numerator on the left-hand side and bring the 6 down to the denominator on the right-hand side. So now it's 5.9 times 10 to the minus 7. Not minus 7, sorry, just 7. And then we can now simply calculate, right? So take 5.9 blah, 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 divide it by 6. Okay. So we get a value of approximately 9.8, right, times 10. Let's see what it's raised to. Looks like it's going to be raised to the 6. Okay. And remember, that's in years. So that's about 9.8 million years, or almost about 10 million years. Now remember, this isn't really the answer because I didn't take into account significant figures right now. Look back at the calculation, right? I had 2 sig figs here in the numerator, 1 sig fig in the denominator. Therefore, my answer should have no more than 1 significant figure. So I would have to round this answer. The 8 would round the 9 up to a 10. So it'd be 10 times 10 to the 6th. Or in other words, it would be 1 times 10 to the 7th years. And that would then be the final answer. So guys, thank you so much for tuning in. I hope this helped. And if it did, please remember to subscribe. I'll see you guys next time.